Chapter 11, we're going to take a look at solutions. First, we need to remember what a solution is. And we learned back at the beginning of the year, solutions are homogeneous mixtures of two or more substances. Then we need to be able to quantify how much solute we have in our solution, and a variety of ways we can describe that amount, and those are the terms that are listed. Molarity is most familiar to us. We learned about molarity a while ago, so let's just make sure we remember the definition of molarity. Molarity is the moles of solute, and its solute is important per liter of solution, because each of these quantities is going to define how much solute we have a little bit differently. Symbol for molarity is a capital M. Next, we're going to look at something called molality. In here, when you're saying and when you're writing it, it's important A, to write clearly, and B, to enunciate, because molarity and molality look and sound the same, but you describe the proportions of solute in your solution differently. Molality is moles of solute, so the numerator is the same, per kilogram of solvent, and that's where the different comes in. Molarity, we're looking at solution volume. Molality, we're looking at solvent and the mass. The reason we talk about molality is it does not depend on temperature. Molarity is temperature dependent because as the temperature of something changes, if it's a solid or a liquid or a gas, its volume can change. So if I had drastically changed the temperature of a solution, I could potentially change its molarity. I will not change the molality of a solution because it depends on mass, and mass is temperature independent. Term that's rarely used anymore, and that's normality. Generally, we talk about normality when we're talking about acids and bases. Normality is the moles of hydrogen ion, or it could be moles of hydroxide ion, per liter of solution. So normality is really just a subset of molarity, but we're looking specifically at hydrogen ion concentration or hydroxide ion concentration. Mass percent is another way of looking at a solution. Mass percent is simply the mass of a solute divided by the mass of the solution. Finally, mole fraction. We looked at mole fractions already when we talked about gases. Mole fraction can work for any substance, solid, liquid, gas, and generally we're looking at mole fraction when we're talking about solutions. So mole fraction is the moles of the solute divided by all the moles in solution. Symbol for mole fraction, if you remember again from gases, is the Greek letter chi. And there we have the different symbols. Forgot to mention for molarity, we have capital M. For molality, it's a lowercase m, and I usually try and make it somewhat of a cursive m. Normality, it's a capital N. There really is no symbol for mass percent, and we've already seen it for mole fraction. One of the things we're going to take a look at is solubility, how much of something that will dissolve versus a rate of dissolving, how fast something will dissolve. So if we look at rate of dissolving, first of all, what are some things that might affect how fast something will dissolve? Well, think about what you do to get something to dissolve faster. You can stir it. If you have small pieces versus large pieces, they tend to dissolve faster. So if I increase the surface area, that will increase how fast something dissolves. Stirring essentially does the same thing in that you're bringing new solvent in contact with solute when you stir something up. You can also heat something up and it will dissolve faster, many times. The things that will affect how much of something will dissolve or the solubility of something, there are two main things that will affect the solubility of something. First one is heat. As the temperature increases, then the solubility will increase generally for solids and liquids. If you think about soda, soda is a solution of gas dissolved in a liquid. If you heat it up, will you be able to dissolve more gas or less gas in your solution? And hopefully you realize that one of the things that happens is if you cool down a soda, it'll stay carbonated longer. Heat will decrease the solubility of a gas in a liquid. As the temperature increases, the solubility decreases for a gas in a liquid. Pressure is also a factor when you're looking at the solubility of gases, which is why soda and beer and champagne are pressurized. The higher the pressure, the greater the solubility of a gas in a liquid or a solid. Vapor pressure, again, is the pressure of vapor above the surface of a liquid or above the surface, in this case, of a solution. And the particles that get into the vapor are, in the case of a solution, both solvent particles and solute particles. And as we see, the vapor pressure of a liquid is determined by the nature of the liquid, Also by the temperature. As the temperature goes up, the vapor pressure of a particular liquid goes up. If we take a look at non-volatile versus volatile solutes, that affects the pressure above our solution compared to the pressure above the pure solvent. If we look at our top diagram, on the left-hand side we have pure water. On the right-hand side we have an aqueous solution. It's in a sealed container, so we can't add or remove water vapor particles from our system. Water molecules are going to go from the liquid phase to the gas phase in both beakers. Over time, water vapor will condense back into the liquid, and at some given temperature we'll have an equilibrium between water vaporizing and water vapor condensing. It turns out that if I have a solution, those solute particles are going to hang on to the solvent particles and prevent them from leaving the solution. So water can escape the solution, but the solute can't if it's a solid solute such as sugar or salt. So if we have these two beakers side by side in the container, over time, what's going to happen is the liquid level on the left, the pure water, is going to decrease because water continues to evaporate and some continues to condense in that container. But on the right side in the aqueous solution, the water will evaporate, but it evaporates more slowly and it condenses at the same rate. So condensation in both containers is the same. Evaporation rate is much slower in the solution because those solute particles are hanging onto the solution particles. If we look at the bottom diagram, we can see the pressure difference between a pure solvent and the solution if the solute is non-volatile, meaning it doesn't vaporize more readily than the solvent. So a solvent vapor pressure is 3 atmospheres perhaps, due to the particles banging on the container walls. When I have a solution, those solvent particles are fewer in number because the solute particles are hanging on to them. Since there are fewer particles as vapor, few of them are banging on the walls of the container, and so the pressure is lower, and we see that by looking at the pressure gauge. Here's a pressure temperature or a phase diagram looking at the difference between the solution and pure water. Remember, phase diagram shows us the difference between the solid phase, which is here, the liquid phase, which is here, and the gas phase, which is here, for a substance, or in this case, a solution. The red lines show us the pure water phase diagram. But if I throw in a solute, such as sodium chloride or sugar, what happens is it lowers the vapor pressure between the liquid and the gas. And so we see for any given temperature, the vapor pressure of the solution is lower than the vapor pressure of the pure substance. So when we get to the freezing temperature of pure water, which is right here, we see that water freezes at atmospheric pressure right here. The temperature that the solution freezes is lower. It's right here. That's one reason they put salt on the roads, is the snow, the ice on the roads is below freezing temperature, but it's a solid. You throw a little bit of calcium chloride or sodium chloride, depending on what they use, on it. It causes a little bit of the solid to dissolve, the solid in the liquid. You get a solution. It lowers the freezing temperature of the solution, and it keeps melting the ice and the snow. So eventually you get this liquidy slush rather than the solid ice, and it's easier then for the sun to evaporate it away. So vapor pressure of a solution in general is lower than the vapor pressure of the pure liquid, especially if we're talking about non-volatile solutes. We used to get into freezing point depression, boiling point elevation, which is the reason you put salt in your water when you're boiling it to make pasta. You get it to boil at a higher temperature, and so it cooks faster.